Good afternoon again. Thank you for attending the first day. And what I'm trying here to do is to create some sort of synthesis from what we've heard today to extract hopefully a couple of messages that we can take home and use in the future in our activities at ADIA Lab. So let me first thank all the speakers for visiting and giving outstanding presentations. And I prepared a couple of questions that I'd like to ask the speakers. And since we have so many, total of 8, I would like to ask the speakers when they answer the questions to be brief. And my first question that I would like to ask all the speakers, and I would suggest that we just go from the audience perspective, from left to right, that is start after me with Steve and then Torsten. My first question is, tell us something that you have learned today, something new that you didn't know and that got you interested. So,
I just learned in the second to last session that there were some computer simulation things that would be very useful in the ultrasound imaging work I am doing for aperture synthesis. As another part of me that I didn't talk about, but that was very interesting. And so I will be very brief and just say that it's remarkable how science crosses over radically different disciplines.
Okay, well, I guess we were symmetric. I learned something in your talk, which very much surprised me, on the greenhouse gas emissions of food production, which usually we talk about travel, we talk about energy production, but actually the food production is something we probably seriously need to check into. So thank you very much.
Me? It was wonderful. Can you hear me? No, it's on. Well. Yeah, I am. It was wonderful. Okay, all these different perspectives and stuff. I think we're in good hands. Yes, it was great. I learned too many things. You want it short, so
pick one.
No, it was great. I mean, the general feeling for me was fantastic.
So I would say it reinforced my feeling that climate change is very important. It's also reinforced the ideas that machine learning and AI are going to have a tremendous impact on so many fields that we are dealing with. And that if I just had to pick, risk management is another thing I guess I learned something about today during the course of the discussions.
Okay, for me, I will start from the quote from you, Luis, but it is actually applicable for every other speakers. It's the transition from no data to many data. Was like many data, but I think what we are all working, while we are from very different background and then skill set, but what we are actually working on is making this more data into more actionable data. I think this is what we all trying to do in different fields. So that one was a big takeaway for me from today. Yeah.
You're getting a double vote because I was very impressed, but many other things, but I was very impressed by your third to last slide when you showed by country, let's call it a sustainability index. I'm sure you're going to give it a different name. If that could be translated either to industry sectors or to companies, then it would do a lot for the problems that you are grappling with.
Yeah, and much of the same. I mean, I think Luis gets 3 votes on this. I like also the topic of social fintech, as you name it. I think the adjective social is very crucial, very important, relevant to be defined, and I think it has much to add to this debate of climate change.
Thank you. So one short, catchy phrase that was used twice today, so I repeat this, is that text is data, and I've heard this used by at least 2 speakers, so we should keep that in mind as something as we go forward. Now, if you consider the confluence of big data, AI, and computation, which is what we're looking at here, where do you see some opportunities of bringing these together in terms of research challenges that we could undertake? Anything that you would like to add based on your experience, but also in terms of what has been said today?
I think when you talk about data, not all data is equal, and the independent data I'm a big fan of. Very quick anecdote. After remote sensing of methane, laser remote sensing of methane was widespread, and that with lasers, drones, and things, all of a sudden we appreciated more how much methane was being emitted, many things like that. And so the self-reporting has always been very scary to me. And the better we get the satellite data, the remote sensing data, all these things, then all of a sudden the data gets better. You can do all the analysis on crappy data, but you need the good data.
So I would say there's one very interesting opportunity to revolutionize the scientific method itself by having these models start to discuss with themselves. Like we are discussing now, we could instantiate different models with different personalities to have a discussion about, for example, societal aspects of climate change and things, because these models, every single of these models knows more than the collection of us about what society is made, and I mean the large models. So that would be an interesting experiment to do, to just have them speak to each other like we do.
Well, yes, your statement about data is very, if there was a universal database for data, that would be wonderful, right? Because then on that, you can build your own version of ChatGPT, and then the data is there, and then we're going to be removing a lot of opinions from this. And of course, I'm a mathematician, and this is, a dream for a mathematician, where the opinions are just left out of the room. However, the social element is still there, and I wonder how that's going to come up. But I think a universal database would be wonderful.
Yeah, I like the idea of a repository, a database for collecting things. We also need some way to reduce or to minimize that in some sense and extract a certain amount so that we don't have to contain all of that data over a long period.
Well, I mean, as a researcher, we've been dealing with a lot of bias, like many type of biases every time, like for, decades, like we've been, try to defend ourselves, our research that, using company self-reported data. And then later, then we were also defending the robustness of the third-party reported data. I mean, that was like one step forward, but, these days, we are getting, new type of data that is kind of eliminated from the human bias into it. So I think this is a very interesting change. I'm really up for this, global data repository thing, but, we really have to think about how we can facilitate the governance of that data system, because while the ones who is collecting the data will be completely off human, but the structure of the data will be again, like human biased. So I want to see, I want to see more discussion about how we want to do good data governance over this data, global data, public data thing. Yeah.
From my perspective, I've been struck that today we have spoken about basically one aspect of climate outcomes, which is stopped, if you want, at the physical part, of the temperatures. But this is just the beginning. It is actually the area where we have, relatively speaking, the greatest confidence. I see an enormous amount of added value by using big data for the second part, or the third part, which is the damage function. At the moment, damage estimates for the same temperature, so even if you all agree on the temperature, The damage estimates are absolutely all over the place. And if we had more time, we talk about all the methods. The method at the moment, the econometric method, the enumerative method, they are inadequate for the task. So the dispersion becomes enormous. Geographically, with high geographical resolution data, it would make I don't hate the word, quantum leap, no, I'm not going to say it, a major advance. It would be the greatest improvement. In all the studies I have done, the greatest bang for the buck is by improving the quality of damage data assessment. And I think that there is an area where a lot can be done.
I totally agree with what has been said so far, and I fully agree that you can have millions and millions of observations and really bad quality data. That's why it's so important to talk about quality standards and data standards and establish them openly, because indeed we need this human aspect. We have to have it. We need to understand what is the importance of subjective damage versus objective damage and subjective risk versus real risk. But we have to have it, but we also need standards. So it would be wonderful to look forward and think on standards that qualify a data set as a reliable data set, independently whether it comes from Twitter or elsewhere. It's an example.
So Luis wanted to say something.
I feel the urge to say something, okay? Can you imagine trading stocks in the 17th century without accounting standards? Can you imagine that? Well, but now things work. You can trade the stock in a millisecond because accounting standards are there. We know about earnings. We know these things are reported. And imagine a company does, bad reporting. You go to jail, right? These things. I think having standards is very important, and then everything becomes a lot easier. So, of course, it took 100 years to get that done. Let's do it 100 minutes, maybe.
I also want to add something. I think I'm the only physical scientist in this group, maybe not. As a physical scientist, I want to make measurements, so it's not data bank things. It's actually how do you actually make the measurements and how good are the measurements. The other thing I want to make a comment is on damage and financial damages. The floods in Pakistan, if you did financially how much damage there was, in terms of money, it's very different than damage to the people. Yeah. And economists are very good at saying, a life in Pakistan is worth far less than a life who lives next to Wall Street. So I think there's other issues that we also have to fold in.
Back to the data, right? Once you have what is data? You don't need to have a single currency. You can have lots of different currencies. And once data is there, you can choose how rich it's going to be. And again, data is not only numbers, right? And then there's a lot of subtleties in the data, like a house, a life, a cat. They're all data points in the database.
But this is the nice thing that these large language models can actually give us, because what we are just having here is an ethics discussion. And one interesting question is, how does ethics vary across cultures? And there's actually huge variation across cultures. But what we have is an unstructured data set that is open, that is called the internet, where basically every culture has a stake in, and we could train a model, for example, as an ethics assistant, or something that gives us the average ethics across all humans that we can ask questions to. So that's just an interesting opportunity that we should not lose sight of, because much of the data, I support the data argument, but much of the data is unstructured and we don't understand. It's not all as clear as a stock market thing that is highly regulated. Most of the data we have is very unclear what it actually is and means, like the measurement.
And going on that, as spending 30 years in single molecule biology, the average of a country, it doesn't tell you what's really going on. It's the distribution. And so that's also something that we have to understand. In the United States, there's a bifurcated distribution of ethics and opinions, I think, or maybe, more than just two.
Yeah, I should say that as a mathematician, the average is not data.
We're in total agreement. I was a math major when I was an undergraduate.
And as a computer scientist, I can say we can actually represent the data fully in computers without understanding it. So we don't need the average. Averages are just human vehicles to understand things, making assumptions about probability distributions, which we don't need to make anymore. Non-parametric statistics all over.
Yeah.
Well, thank you for getting a good conversation going. So I think at this point, everybody has warmed up a bit. So then I would like to open it up to the audience to ask questions. We didn't ask any questions throughout the day. So maybe there's some questions that were on your mind that you would like to ask individual speakers, or that you want to pose to the panel in a general sense. So do we have a microphone going around?
Steve, you went very fast the last few slides, and I would like to maybe if you can spend a few more minutes on them, and what sort of technologies have the potential to do something within a certain time frame that's practical in a way.
Let me start with the hardest, agriculture. And the fact that we need to nourish plants to feed 8 billion going to 11 billion. And I myself am starting to do some of this research. The N2O emissions is particularly problematic, even more so than methane. And so it's possible, and this is fertilizer that you put in the ground, and the plants capture at best 1/4 of it, and the rest of it is nitrates turned into N2O, which goes out. So it doesn't even go to streams. There's streams we could have gotten it out. And so there are two strategies. The strategy number one is, can you put, when you plant the major grains, corn, wheat, rice, everything, and at the rhizomes, the border of the roots and the soil, there are self-fertilizing plants that have inspired people, like legumes. You put microbes that then enter into a symbiotic relationship with the plant, and they take the nitrogen out of the air, and you begin with nitrogen, but phosphate all the other major ingredients and feed it to the plant. Okay, and so you're now adjusting the soil biomicrobiome. It's not completely science fiction. I was part of a company that did some molecular biology, synthetic biology, to make microbes that eliminated half the fertilizer of corn, which is very fertilizer intensive. It took too long. My company went bankrupt, that I was on board of. And so that focused me on saying it took too long, but so you do one gene, one promoter at a time. So I'm developing technology that hasn't been published yet, where you can do 10 genes at a time, massively parallel. If you do that, then you can type out the DNA. And so you can do massively parallel experiments till you can turn around things in 1 or 2 years, not 10 years. And you want to do this for all the major crops. The other thing is another microbiome thing, and that is look at the microbes that turn the nitrates into the N2O and see if you can alter that. Okay, this to me is one of the hardest problems. There's others like that. Carbon capture is an enormously hard problem, in part because the energy penalty. And it just costs too much. And in order, if we had a price on carbon that's $500 a ton, that's okay. But if it's $100 a ton, you're not going to capture anything from the air. And the prospects. So either you make the price up or you get the technology better. And so that's something that needs to be worked on. The energy penalty especially is the big driver. And so again, there's some smart people. And I can go down the list of things, but one final thing, I went very fast in this. We will run out of copper. We've already running out of nickel and cobalt, so the EVs are already transitioned to iron phosphate. Okay, but lithium, I went fast. We figured out a way to mine lithium from seawater. So for EVs, it's not going to be an issue, but copper is an issue. And that's why I talked very briefly, can you get methane out of the ground into carbon that's a high conductor cheap? Because there's lots of carbon in the ground, and that doesn't harm the environment. And if we can do things like that, if you can get all the carbon in the ground to start to replace structural things, steel and concrete, we will we can decarbonize some of the steel. Hydrogen would be a good thing. You don't have to have the coking process. Carbon capture is essential from point sources. That's probably, but the atmosphere is something very different. And so I've, over the last couple of decades, been looking at the hardest problems, going out and talking about it, but me, myself, saying, I will think about it too. And the more people understand what's material, and right, it's not a cute technology, it will never scale. That's the thing that we have to get the technological community focused on, and finally for the policymakers, the right financial understanding and incentives to actually get the policymakers to say, this is the right policy that can actually move the needle, because without the policymakers, the technology is going to be useless.
Can I make a comment here in answer to your question? There are many splendid ideas which I regard a bit like moonshots. They're extremely promising, and they might work or they might not work. At the moment, there is an obsession with the renewables. Don't get me wrong, renewables must be pursued, done 100%. But there are existing technologies which at the moment do not enjoy the same level of subsidies as renewables. I'm referring, for instance, carbon sequestration and storage. Technology has been around from the 1930s, is not dramatically expensive. If subsidies were put in that direction, efficiency gains would bring the prices down massively. At the moment, there is zero incentive, even if the costs were $1 per ton, there is no incentive for doing it. So it's great to have lots of brilliant ideas and fusion and lots of things that might come to fruition. But there are technologies which are now available. Basically, we said everything is emissions, everything is concentrations. So if we take out, that's what matters, is the concentration, not the emission. So absolutely, renewables must be increased, must be made, but we have, as the IPCC very clearly said, there is no hope of getting 1.5 or 2 by the end of the century without somehow removing. And the technologies are here. So it's great to look for moonshots, but we should also keep our eyes on the things which are available already, and they just have to be properly subsidized to become commercially viable.
I think the United States is doing something to try to do this, and I agree with you completely that renewables is only a small factor of what's going on. You've got to do something about the carbon from point sources and eventually really from the atmosphere. There is no market for any of this stuff. So all the transitions we talked about, all the energy transitions, they were actually better solutions to market needs. And all of a sudden, there is no market for carbon pollution. And so that's a fundamental change the world has to make. It has, especially in the United States, has not made that change yet. And so without a market, you need governments to actually say, this is what we're going to do. And so if you can turn it into a market, then that would be fine. But there's a total absence of a market. Oh, by the way, a price on carbon, it's one of the tools. $100 a ton in the United States will raise the price of a gasoline about 50, 60 cents. That's not going to change American driving habits. What changed European driving habits was tax. Okay? So you can't be only incentives. If there's no sticks and you're just giving out free money, that also won't do. And no politician has the courage to give in sticks at the current feeling. Okay, only carrots. And so that's like saying, pay me not to chop down a forest that I wasn't going to chop down anyway.
Thank you for the organization. It's really a nice event. I enjoy here a lot. And we're talking about climate change all day, and my question is related to the energy efficiency about the current large language model, for example, or current traditional neural networks. we know they can give good results, but at the same time, they consume a lot of energy and a lot of water and a lot of money. And on the contrary, there are some new techniques like new algorithms or new architectures, such as the brain biological inspired neuron models or biological inspired spiky neural models. They are energy efficiency, and so in terms of energy consumption, what do you think of these new technologies? Thank you.
So I guess that's for me. Yeah, thank you for the question. That's actually a great question, because there's something very strong to be said in favor of these models in terms of their energy or their CO2 production. So these models, as we all know, they are trained on very large supercomputers. These supercomputers require a lot of energy to run. I mean, Jack has given us the exact numbers, 22 megawatts or something like this. They're trained for weeks at a time on these supercomputers, yes. So it is said that one of those models approximately requires the, or outputs the amount of CO2 that a car outputs in a lifetime. So, okay, so for one model, that's a number, it's one car. How many cars do we have on the street? A lot. So in Switzerland, there was actually this joke at some point when we had the energy crisis 2 years ago that, well, should we turn off the supercomputers? Well, members of the government came and said no, because one train runs at about 20 to 50 megawatts, so we can just turn off one train. The supercomputers are more important. But there's an even stronger argument you could make. Yes, it's a lot of CO2 we are generating, but in the overall set of things, it's a small number. But now, these language models, once trained, they can do creative work for you. There has been a study recently that compares the CO2 emission of a human writing a page of text or drawing an image. By the way, all of the images, all of the drawings in my slides were AI generated. They were generated in milliseconds. Like each of this drawing, like these clouds and all of that, that's a millisecond. Put a human at work to draw one of those clouds or write text, that's about a factor of 10 to 1,000, depending on the human and the AI model, more CO2 emissions per generated artifact. So training is expensive, but using them, in fact, saves factor 10 to 1,000 compared to a human doing these tasks as we would be doing today. So there's something positive to be said as well for these kinds of things.
Actually, I'm going to defend biology a little bit here. If you think of a 4-year-old whose parent speaks one language, another parent speaks another language, and they're rich enough to have a nanny who speaks a third language, by the age of 3 or 4, that child is fluent in all 3 languages, has done pattern recognition, doesn't need the large data sets to figure out a lot of things, probably on 10 or 10 watts. And when you're an adult, you're 20 to 50 watts, depending on how smart you are. That's it. And so if we can emulate what's happening in a human brain, and so you do not need as large a data set, that would be wonderful. Now, having said that, there's another part of your question, Sub Rosa, because once trained, yes, but the 3 companies in the world that have the assets, Amazon, Google, Alphabet X, and Microsoft, are the only ones that get bigger data sets to make it even more powerful. And there's the stragglers behind who are saying, well, with the stuff we have, we can make it more efficient. But there are only 3 players, and that's gigawatts and higher. And so that's a little scary. But the other part of the question is, the machine learning stuff is good. I'll tell you, in my humble opinion, the worst part of this is, I don't know if it's true, I have to triple check it, but I'll just say, take it with a grain of salt. But half of the compute power today is for cryptocurrency and mining cryptocurrency.
That should be forbidden.
And what are the first applications of cryptocurrency? Money laundering and financial fraud. And, you know, I think countries should take a little leadership position and ban it. This is ridiculous because you know, it started idealistically, you would have something, you could bypass visa and all this other stuff, but what really happened was it became the worst thing possibly imaginable, and it should be banned.
Absolutely. Yeah.
So
Half of the energy of compute, which is 6% of electricity.
So now we get into an argument. So, well, I completely agree on the biological brain, but we have to be very careful because you just mentioned we don't.
You're going to argue about cryptocurrency.
Oh, no. I think we totally agree on that, Steve. But the one thing I want to argue is how humans learn, how we learn, how language models learn. If I would take your child and for hours and hours and hours would throw random text at it, your child would not learn the language very efficiently. That is the problem. So the way we teach models today, we don't do curriculum learning. We literally throw random text at the model and expect the model to figure out what's going on after a while. It's incredibly inefficient. This is due to the thing that you mentioned, that we don't really have algorithms. Actually, I totally disagree. We have a lot of equations in deep learning training. I mean, stochastic gradient descent is, but
equations are okay.
There we can argue another time, but the point is that we are missing the priors. I mean, machine learning people call these the priors, the structure, how to learn things effectively in today's methods. We really do brute force. We have the compute, we have the data, we just throw a relatively simple model at it, we just run it through. We are supercomputing people, we do it great. It works actually, but it's not as efficient as it could be. So there is a gap there.
I don't think you were arguing with me. You're just saying that the machine learning today could be far, far better, and we can approach a child's brain
Yes.
with much more horsepower. I think that's what you said, right?
Yeah.
For the record, equations are good.
Oh,
I love equations. But there is something to be said for the fact that if you have large data sets and you don't have the equations, and this is what large machine learning has really taught us, and there is some power, a lot of power in that.
There's actually, maybe I should remind everybody of a sentence by Richard Feynman, which is one of the unreasonable usefulness of mathematics is that the same equations have the same solutions.
Okay, but we're going to be philosophic here. I find that the fact that you can have mathematics and equations to describe the physical world, and logic was an experimental discovery. Okay, I'll say it again. Logic is an experimental discovery, and it's an experimental discovery like the second law of thermodynamics. It seems to work. And from that, the logic of equations seem to work. Okay? But what those were discovered. Mathematics is discovered and logic was discovered.
I will take that one further, if I may. Actually, that is super interesting because at the end, all of these equations, what they do, they compress. At the end, it's all about taking the unstructured knowledge we have and compressing it into a structured framework such that we can reconstruct the seemingly unstructured nature with our structure. This is what we did empirically over ages. We invented logic as humans. We invented number systems. We invented equations eventually. We invented all of these nice things. Fun fact, the language models now, as they grow, they have invented first-order logic themselves by throwing random data at it. We can prove that today in the language model we have a vector for cat and the vector for not cat. That is first-order logic. It is extremely fascinating what these models do, and you know why they do it? Because we force them to compress. Humans have been forced to compress, or not forced, but they had an incentive to compress. Right. It's all about compression. Like, literally, it's all about compression.
I think in my university, Faith Lee had something to do with the cats and dogs and fire hydrants. I know her very well. She's a friend of mine, but machine learning is redefining what we call understanding as well.
We have one question from the online audience. So the question is, is quantum computing any near to be applicable in the environmental sciences?
Was the question, is quantum computing going to be?
Yes. So the question is quantum computing any near to be applicable in the environmental sciences?
when quantum computing becomes applicable, and yes, and I would say first we've got to get quantum computing to do something that normal computers don't do, and number one, and then if it does become a really powerful compute machine, then you can do, 1 kilometer, less than a kilometer simulation in a year a day, maybe, but we're so far away from this.
I'm a little bit more skeptical here.
I was pretty skeptical.
I see. Well, Nir, it's a great question. I mean, first of all, I want to disagree. We're on a panel. I have to disagree. Quantum computers, in fact, do something that classical. Excuse me?
You're the 10%.
Well, it's called a panel. So quantum computers, in fact, can do something that classical computers can't do. They can solve random quantum systems. The question is, can they do something that people would actually pay money for to have a solution to that problem? And the answer is so far no. So we again agree. I just wanted to clarify. But would they ever do climate simulations? That's an interesting question. In fact, me and my colleague from Microsoft wrote a paper about this a while ago in CACM. And the answer is unlikely, because quantum computers are fundamentally limited by their capability to process large amounts of data. They can have a very large state, but they can have very limited access to classical data in terms of inputting it, and outputting is even worse because your quantum state collapses, and then you take an exponentially large quantum state and output a polynomial size data state, which is quite bad. So there are seemingly fundamental limits due to the structure of quantum mechanics that we must consider when making these statements that we may be doing kilometer scale climate simulations, because remember, kilometer scale climate simulation is a 500 million element thing at least to just tile the Earth. So reading that into a quantum computer is going to be challenging.
No, actually, you're right. I was wrong. I think the first application I would see is in some drug design.
Well, absolutely. Yeah, the Haber-Bosch process, for example, that's a great application. Many physics simulations. Yes.
They will be good for equations. Yeah, they're good for equations. Certain equations.
Certain equations, right?
Not data.
Jack?
Yes, well, let's see, I'm skeptical of, so I'd say quantum computing is a great research area, and it has a lot of promise for the future. And I think it'll continue to have promise going forward. I don't see quantum computing replacing our computers that we have, at least in my lifetime. And I would say, there's many obstacles that we have to overcome before they become a real useful tool. But again, I think there's great promise there, and we should invest in understanding and trying to sort out what the positives are and the negatives are. Thank you.
And they have a huge potential area of use that we shouldn't undermine here. They're just not good at data processing. But what you just mentioned, I mean, all these processes, this could be amazing.
Okay, there's a question all the way in the back. Yes.
So there's something I wanted to point out, is that for large language models, inference is also very expensive. So if you are doing some basic search using Google, is significantly more efficient and less computationally expensive than using a large language model. That's one thing. My question is regarding using physical priors for machine learning models, and there have been some papers in recent years about that, and it seems like a very exciting topic. Have you, any of you guys, worked on using such algorithms for machine learning using physical priors, and what was your experience with that? Thank you.
A lot, actually. I mean, in my talk, I was probably way too fast. In 15 minutes summarizing 3 years of work, that was a bit much, I guess. But all of those models have strong physical priors. I mean, even the standard CNN is somehow a physical prior that only the immediate surroundings matter for the interpretation of an object. So we always have some kind of prior in the model. So you're asking about specifically physical priors, maybe in climate sciences. So that was the thing that I had to explain in 3 minutes. We assume we live in a Fourier basis. So we take the signal, the data, and put it into a frequency space, and now we chop off at a certain frequency. So that is something that represents the cyclic patterns, seasonal in time, but also in space. There are certain cyclic patterns that are very, very important in physical sciences. It's a Fourier operator. But the Fourier operator has the problem, and again, that was like a 2-minute part of my talk. Fourier operator has the problem that it smoothens things, right? Because it's Fourier, it's nice and smooth, it's all waves. And this is when you want to go to wavelets, because wavelets have the wonderful approximative property, but they can have sharp corners as well. This is very similar to what we do in image compression today, like JPEG compression and things like this. They're also in a wavelet basis. You can now apply that in the learning context, and people do that. So yes, very strong physical priors are needed to drive this forward. Equations. Somehow the question is, how can we put our equations in the model? Nobody really knows how to do this.
Physics-informed neural network.
Exactly, pins. Yes. But so far, purely data-driven methods have been far more successful than any form of pin for short-term forecasting as well as long-term forecasting. So yes, these models exist, but they're not as practically successful as to just like take a hammer and data models, and we don't really understand why. For example, the models that conserve all the physical properties, which is a strong requirement, don't lose energy over a couple of days in the Earth, right? They perform much worse than the models that do not conserve these physical properties explicitly. So we know that the machine learning models we use today lose physical properties, but they perform really well for prediction. It's an interesting field to look into. So we are just at the beginning of this, is what I'm saying. A lot of open questions, and the question you ask is the perfect question to engage in research in this area.
Thank you very much.
I have a question for the simulators, modelers. The biology part and the biology feedbacks. What is being done about that? Let me give you a short example. The ocean's being acidified, and one is worried about lots of things: heat, coral, microbes, everything like that. And so people have done experiments where the phytoplankton, they just make it more acidic, and of course they die. But historically, going back to my history lesson, I just went back and said, okay, there was a time long ago when carbon dioxide was much higher. What was happening? They flourished. So it's the speed of evolution that matters. and so how are you putting this into these models going forward in time? Because it's the evolution of the whole ecosystem. That's my question.
We need equations for that. We don't have them.
Even empirical data, I would be happy with.
And I don't think the data can help us there.
For the speed, you can do something. If the doubling time is a day, evolution will take care of it. But there's other parts of the ecosystem where the doubling time is not a day. It's much, much longer, and there, evolution will not take care of it.
A second thing I learned, or it was reinforced in your talk, you basically said we need a certain form of stability to enable development, to enable evolution. If we are in a very chaotic system, very chaotic environment, no evolution will happen because the rate of change is faster than the rate of adaptation, and thus nothing can develop. So somehow, this is exactly the speed of change is the problem. So is there, one of the questions to be asked here, is there a natural constant how fast evolution can adopt or not? It seems to work on a relatively slow pace, and you see this in societies even, that some develop faster and some develop slower, and very much is given with the stability of the society in that context if you look at social scientists. So we would need to understand that maximum rate of change that is admissible, and whether we are exceeding that maximum rate of change with the current developments.
Yeah, there again, where it's microbes, it's fine. If the people where the doubling time is 25 years or something, you've got a real problem. Because you need many generations, many random experiments to find the solution.
But we have technology now. which is an interesting
Speed to
factor.
random selection.
No, we don't need random selection. We can guide random selection with technology.
Are we talking about altering the germ seed of humans?
Yes.
I
Oh,
thought I
biology.
heard right.
Or CRISPR.
Yes, that's true. I have no problem altering the germ seed of microbes and plants. You know, we should pause a little bit when we think about humans, because if we make a mistake, it's hard to do a recall on the product.
Okay, I'll ask one more time for questions. Please raise your hand. Are there any questions on the remote viewers? No? I think this is probably a good point to thank one more time our speakers for a very lively exchange, and I hope you take a chance again to talk to the speakers and explore what questions you still might have. Thank you.